My name is Roland Pieruschka, and it's my pleasure to host a panel discussion about tackling climate change and environmental challenges. The reason for the sessions, it's very obvious. Humanity exploits natural resources to sustain growing. There is a growing demand, hunger for energy, etc., etc. Then, therefore, monitoring the environment, understanding the Earth system processes, understand the hazards of natural resources, and management of those resources, it's becoming more essential, actually. Thus, the session or the panel discussion will focus on research infrastructure that address the key aspects of the Earth system sciences with geosciences on one hand, atmospheric sciences and marine sciences, such addressing basically the key elements. After each session, so there will be 3 presentations addressing these 3 different domains. After each presentation, there will be time for some questions. Please feel free to put your questions into the chat or raise your hand. After the 3 presentations, there will be a short panel discussions where we will have the opportunity to discuss in more detail about the presentations. And as such, I would like to start then with the first presentation by Tim Rawling. So Tim Rawling is the CEO of AuScope. AuScope is the provider of research infrastructure to Earth science and geospatial science community. Tim has a strong background in structural geology, regional crustal geology models. He was involved in exploration, development of implementation of exploration methodologies, and as such, without much ado, I would look very much forward to the geoscience research infrastructure in Australia and beyond. And Tim, the stage is yours.
Thank you very much, Roland. I'll just try and share my screen. Are you getting my screen, anyone? You seeing the slide, Roland? Can I just check? I can see you.
Not yet, Tim. We see your background. Oh, no.
Yeah, it works.
Thank you.
Okay, sorry, you've got it? You can see the slide? Okay, great. Well, look, thank you very much, Roland, and thank you for those that have put this conference together. It's fantastic for me as somebody who loves traveling to Europe and working with our colleagues in Europe to have this opportunity, because I've got to say I really have missed it the last couple of years. And just looking at that slide in the background on Roland and the organisers, where they've got Australia mapped just below Spain and Italy and Greece, and man, how I would love that to be true. But, you know, it's not. And so there is the tyranny of distance, as Carolyn mentioned, that hopefully we can overcome with more meetings like this. So as Roland said, I'd like to give you an introduction into AuScope and the research infrastructures for the geosciences in Australia and the role that we play, which is kind of unique. But first, I'd like to start by acknowledging the traditional owners of the land. Excuse me for 1 second. There we go. I'd like to acknowledge the traditional owners of the land on which our research infrastructures and communities operate, and on which we virtually meet today. For me, that's the Boon Wurrung people of the Kulin Nation, and I pay my respects to the elders past and present and recognise the connection they have with the land, sea, sky and waterways for tens of thousands of years. So I'd like to start by giving some geological context for the geoscience research infrastructure investments that we have in Australia. So if we start by considering that Australia's unique geological setting provides challenges and opportunities to this part of the world. We live on one of the most remarkable geological environments on the planet. Australia's continent is huge. Our land and marine jurisdiction is enormous. It's the Earth's fastest moving continental plate. We have active margins where new crust is being created in the south and where it's being destroyed in the north and the east. Our plate has a long history of mountain building and deformation, which has led to the formation of highly fertile parts of the crust for both minerals and energy deposits. And this is something that our national prosperity has been strongly influenced by over the last 150 years. The crust is also old and weathered, which means that many of the deposits are hidden beneath shallow cover sequences and are very, very difficult to find. And this presents one of the critical research challenges that geoscientists face in Australia. As we strive to achieve net zero emissions, we need to substantially increase domestic supply of critical and battery metals, including copper and the rare earths. In fact, in the next 2 decades, if we're to build the green power generation and storage capacity and electric vehicles that'll be required to hit those targets, we're going to need to find as much copper as we've mined in all of human history. In terms of copper alone, this is the equivalent of finding a new Escondida mine, the largest copper mine in the world, every year for the next 10 years. And bearing in mind, we've only ever found one of these, gives you a sense of the challenge that we need to overcome if we really are to try to address these net zero 2050 challenges. As population grows and the climate changes, understanding the complex systematics of our groundwater resources in Australia is also becoming more and more critical. We live on a very dry continent, and that water resource is going to become more and more valuable over the next decade. So here lies an opportunity that will rely heavily on research and technological advances to be realised. We also live on a highly stressed piece of the Earth's crust. We don't really have a good handle on the risk associated with geohazards in this place. We have a long and recent history of volcanism and earthquake. Those of us who live on the East Coast were shaken by a magnitude 6 earthquake the week before that. And the first Australians would have experienced significant earthquakes in excess of magnitude 8. But because of the intraplate setting and our modern observation record being so short, we haven't really fully characterised this risk. So there's a lot we don't understand about living on the Australian plate. At the end of the day, AuScope is a research and technology enabler that allows geoscientists to investigate how the planet works, how it changes through time, and the crustal services that it provides to us. And this allows us to understand human impacts on the Earth and its changing habitability. So AuScope was established in 2008 to develop a national research infrastructure capability for the Earth and geospatial science communities. And it was funded largely by the National Collaborative Research Infrastructure Strategy, or NCRIS, which you've heard many people talk about over the last few days. We're an integrated infrastructure that includes field-based observational infrastructure deployments in geophysics and geospatial, analytical laboratories in geochemistry and geochronology, characterization facilities like high-logger hyperspectral core logging infrastructures, data repositories, analytical tools, and simulation and modeling codes to add value to these data sets. We've got a free data model that's based on economic rivalry principles, where if you provide data that's free to use without impacting on the ability of another to use it, it empowers people, it empowers researchers, and it attracts exploration capital to Australia. AuScope operates as a non-for-profit company limited by guarantee, and we're largely funded by the federal government through the NCRIS scheme, but also receive some financial contribution from our member organisations. To deliver our programs, we work with 21 partners across the country, including Geoscience Australia, CSIRO, the state and territory geological surveys, 10 major universities, and 1 cooperative research centre. We have collaborations with aligned NCRIS organisations, including TERN, IMOS, NCI, ARDC, APPF, and PAWSI, many of whom you've heard from over the last few days. We're also developing international collaborations with ICOS in Europe, IRIS, the US Array, EarthCube, and UNAVCO, and I'll talk a little bit more about that later. We also have outreach programs in place with 50 secondary schools, throughout regional and urban areas in Australia, which is called our AuScope project. And this addresses one of the most significant risks to our discipline in this country, which is the lack of exposure to geosciences for numerate students entering the tertiary science programs. We also have a permanent, semi-permanent and temporary instrument deployment right across the country in Antarctica and in some cases on the seafloor. Our users are really diverse. You can see that while we predominantly serve the academic research community, we also have strong user numbers across government agencies and industry. Our software products are also have huge impact with over 170,000 downloads. Our engagement program, AuScope, reaches 36,000 secondary school students across the country each year. AuScope employs about 85 people nationally, mostly through our partner institutions. As I mentioned, we also have significant observational capability, which includes national passive seismic and magnetotelluric geophysical monitoring arrays, aftershock seismometers, ocean bottom seismometers, very long baseline interferometry telescopes, global navigation satellite system sites. And this map shows the location of many of those deployments over the last decade. Together, these observation sites allow us to image the subsurface, monitor earthquake hazard, and monitor deformation and movement in the Earth's surface and in our plate. And also, importantly, to monitor human impacts on the Earth. We also provide researchers with access to the subsurface through borehole access, long-term downhole optic fibre monitoring sites, and hyperspectral logging of over 1.5 million metres of drill core from across Australia. And these sites show the location of those borehole access sites. So over the time we've operated, AuScope's generated a large number of impact stories. Carolyn mentioned earlier that we try to communicate these. And if you're interested, I would direct you towards our website. You can see the link in the bottom corner there where there are a number of them listed. But there are two that I'd kind of like to draw your attention to because I think that they're really nice highlights of how the NCRIS program's been successful in Australia and how investment in geoscience research infrastructure has been successful. So the first one is the AuScope investment in VLBI, or very long baseline interferometry telescopes, and GNSS geospatial infrastructures. In many ways, this represents an ideal example of the impact of the NCRIS program because the initial investment in the VLBI telescopes and the GNSS sites was designed primarily to support research activities focused on understanding how the plate deforms and the earthquake risk that we have that's inherent in Australia. Geoscience Australia identified this as a future need, but also recognised that it wasn't something that they were able to invest in at the time that we started to build this infrastructure, which was in around 2008, 2009. However, upon completion and when GA started to run this infrastructure, it was recognised that it was critical. And in particular, it was critical to precision location and the development of dynamic datums, which are becoming more and more important as we have self-driving vehicles and things. And when we live on a plate that's charging to the north at 7 centimetres a year, you don't want your Uber deliveries being delivered 7 centimetres to the south each year. In fact, we rely on this AuScope infrastructure every time we use maps on our mobile phones. And it's really critical to spatially sensitive industries right across Australia, like agriculture, as in the image there. In this case, research showed the way. It allowed GA to sell the value proposition, and this infrastructure is now operated with a $225 million Commonwealth investment in the national positioning infrastructure. And some modelling that we did and that Geoscience has done indicates that it'll probably return a $6 billion return on investment over the next 20 years. The second example is the development of the HiLogger hyperspectral core logging instruments and the related national virtual core logger data infrastructure. Mining companies in this country spend vast amounts of money drilling holes into the earth, but usually they collect really limited data when they analyse the samples that they return. And usually that data is just related to the commodity that they're interested in. So This represents a huge underutilized national resource that should be available to the research community. AuScope recognised this, and we partnered with CSIRO and the State Geological Surveys to develop an instrument that cheaply and quickly records images and compositional information from this core prior to it being disposed of. And we developed a database, storage, delivery, and analysis tools to allow researchers to analyse the data. It's now used by industry, government, and academic geologists alike. And we've now mapped over 1.6 million metres of core from across the country. The high-logger technology has subsequently been commercialised by partners at CoreScan, which is a Perth-based SME, and is now being developed for deployment in a bunch of other geological surveys around the world. So what's the challenge for the next decade in Australia? Well, the Australian geoscience community has been considering the most critical challenges facing our discipline and what research focus we'd like to support over the coming decade. As a result of this, a number of documents have been released recently. One of those is the National Academy of Science Decadal Plan. Another is the Uncover Roadmap, which was a jointly developed roadmap by industry and academia, identifying what investments need to be made to support discovery of mineral resources critical, particularly to decarbonisation in Australia over the next decade. Each of these documents identify 4 key strategic challenges relevant to the earth and geospatial sciences around critical mineral security, energy security, water and food sustainability, and geohazards. These also align with 6 of the UN Sustainable Development Goals that I'm sure you're all familiar with. So in order to tackle these challenges, each of the roadmaps agree that there's one fundamental capability that we need to develop over the next decade, and that's an ability to undertake predictive geoscience. So one of the major focuses for AuScope and our investments over the next few years is to make sure that we provide the data and infrastructures that facilitate this predictive geoscience capacity. In response to this, our communities come together to co-design an AuScope strategy and investment plan. There are 150 geoscientists involved in this, 3 working groups that took 2 years to develop. And these documents outline both our organisational strategy and specific project investments that are required by the community. Interestingly, I think from a research infrastructure perspective, we've realised that our community wants us to take on a much more nuanced role than I think we have in the past. We are seen as an unconflicted and honest broker of geoscience data. We're not seen as being tied to industry or government or any particular university. And as such, we're afforded a unique opportunity. And there seems to be a real desire from our community to play a leadership role and perhaps one that in the past we wouldn't have considered to be our core business, but certainly one that my board now recognises as being a really important role for research infrastructures to play. So if you're interested in this approach or our vision, I'd direct you to the link on that slide and you can download either our investment plan or our strategy. The critical outcome from this process was the recognition that to better understand the Earth in 4 dimensions and the processes that operate within it, we need to provide data sets and tools designed to facilitate a predictive capacity. And to do this, we're building a new integrated research infrastructure system that connects to existing AuScope projects and adds a number of new elements, providing capacity to support evolving geoscience research areas. We conceptually describe this integrated system as a downward-looking telescope. The DLT is a distributed observational, characterization and computational infrastructure, providing the capacity for Australian geoscientists to image and understand the composition of the Australian plate with unprecedented fidelity. Like a telescope, it allows us to see into the Earth using a series of lenses. And these are a temporal lens, which sees through time. An observational lens monitors change. The characterization lens examines the property of rocks. We then have a data framework and an analytical framework to model different processes in the Earth. As I said, it builds on the 11 existing AuScope projects with an investment in over 20 new programs. And this is what will focus our attention over the next decade. The DLT will provide geoscientists with the tools required to develop predictive geoscience capacity and will underpin research programs focused on addressing the search for critical minerals, energy systems, groundwater, and to manage the risk of geohazards. I also mentioned our relationships with European cohort colleagues, rather. There are numerous opportunity for collaboration between the existing geoscience research infrastructures. There are established links between AuScope and IPOS, and we're also developing discussions around what would be required to build a global research infrastructure in the geosciences, with discussions between AuScope, IPOS, IRIS, ENVRI, EarthCube, and ESIP, and a number of others. But what I've done here is just mapped out the existing AuScope project along the top, and it might be a bit hard to read, and the IPOS project along the bottom. And I think what you can see is that there's almost a one-to-one match of our programs with IPOS's programs, for those of you that are familiar with them, which is gratifying given that AuScope and IPOS were effectively independently developed at about the same time, with very little communication between us until quite recently, but that is certainly changing now. And we're in the process of developing an MOU with IPOS for future collaboration. So that's where I'd like to leave it. Thanks for your time. I hope this has given you a sense of the AuScope programs and activities and the collaborative approach that we've taken, and given you an idea of what we plan for the future in the development of the downward-looking telescope.
Thanks a lot, Tim. Are there any questions from the audience? I would actually have a question specifically coming with my background from agricultural sciences. You showed some pictures where you had this agricultural field areas, and you also showed this downward-looking telescope. So I suppose you also support agricultural sciences, I suppose in terms of water availability, nutrients, monitoring, observing potentially also the dynamics. I suppose, could you elaborate a little bit more on this? How do you support specifically, from my perspective, my personal interests, agricultural sciences?
So we're starting to collaborate much more closely with APPF and turn to other NCRIS capabilities. One of them around developing drone technologies that are beneficial across all of our different fields for observation, and drone-based data management protocols that cut across what the three different groups do. AuScope, as you rightly point out, is very interested in groundwater, particularly, less so surface water, more so groundwater. But as you say, that's a really critical resource to the agricultural industry. And we're also interested in soils. So we do have some observational capacity around soil and soil evolution. But as we sort of pointed out, there are these different NCRIS capabilities that cover different parts of the geosphere and the biosphere and the atmosphere and the hydrosphere. And we all sort of integrate really, really neatly together. So the agricultural component is more strongly aligned with APPF and with TERN and other groups like that. The specific image that I showed was more around the precision agriculture component of it and providing the dynamic datum that allows automated agriculture to take place as well. Okay, thanks a lot. That sounds very, very interesting. So looking at the time, I would suggest that we move on to the next speaker. So the next speaker would be Werner Kutsch. He's a director of the Integrated Carbon Observation System, ICOS. His background, he's a biologist, plant ecologist, ecosystem scientist, and he has been working on ecosystem carbon cycling for and carbon climate for quite a while. Werner
Werner within CO2, within ICOS, Werner is organizing the operations, the distributed observational facilities, capabilities, and looking at the between different observational program of ICOS, developing data platforms of ICOS. It provides also in situ data on atmospheric greenhouse gases concentrations, on fluxes of ocean, land surface, which is obviously essential for climate modeling. And as such, I'm pretty much looking forward to the presentation on ICOS. And Werner, the stage is yours.
Thank you very much. Good morning, Europe, and good evening, Australia. I suppose you're seeing my slides, and I would like to start my presentation with a congratulation to the 21 physics Nobel laureates, because they are awarded for groundbreaking contributions to our understanding of complex physical systems, and they found the hidden patterns in the climate and other complex phenomena. And I think that's very important, and I would start my presentation with a remark and 2 quotes. The remark is that I think if you go from micro scales to the large macro scales, the complexity in physical systems is not always the same. There are some specific scales in physics where we have highest complexity, and this of course requires highest scientific excellence and also high investment into the respective infrastructure. So we have the subatomic scale, we have the Earth system scale, and we have the universe. There might be another scale, that's the scale of the organism, but perhaps that's more biology and chemistry. But anyway, I'm very glad that the Nobel Prize went to researchers who showed the excellent science at the Earth system scale this time. And there were 2 remarkable quotes that I want to cite because they are like a guidance through my presentation. The one is from Jochen Marotzke, who is the successor of Klaus Hasselmann in the Max Planck Institute for Metrology in Hamburg. And he explained about the Nobel Prize that model calculations provide patterns. And when we find these patterns in observations, we have recognized the human fingerprint. And this is one of the core things that the Nobel Prize is awarded for. And Klaus Hasselmann, in a spontaneous comment, said, "I would rather have no global warming and no Nobel Prize," which is, I think, a remarkable quote. So let's go to the first quote from Jochen Marotzke about models and patterns in the observations. So the models, they of course digest always the current knowledge, and then in the model you can play with complexity and you can filter noise and see trends and patterns. And of course models are used to make predictions and scenarios. I have highlighted one European research infrastructure, ICOS, which is the infrastructure for Earth system modeling, and all these big computational centers are connected there. And then you have the observations. Observations need to be standardized. I think that's very important. And also from the results and the data of the observations, you can filter the noise and see trends and patterns, and the data have to be provided very openly and as fair data. In the center, you see a small graph. Sorry for putting this only so small, with 3 lines. You see a blue line and a red line. These are models or modeling results. The blue line is modeling the temperature increase without any influence of greenhouse gas emissions, and the red line is including the human influence and the human greenhouse gas emissions, and the black line are the observations. And this is one piece out of the Nobel Committee's justification for the Nobel Prize, showing the importance how observations and how models go together to increase our knowledge on the complex Earth system and on climate change. There is one additional interesting remark in the commentary of the Nobel Prize Committee, and it's saying it's something about observations. In the lab, you can make easily experimental measurements to test your theory, but cosmology and also climatology are observational sciences. So practitioners observe that which nature allows. And I think that's an important sentence about the constraints of our observations. And when it comes to the climate system, we have some essential observations to make to understand not only the temperature side, but also to understand the greenhouse gas side. And this includes the global carbon cycle. And the global carbon cycle has 3 active reservoirs: the atmosphere, the land, and the ocean. And there's one passive reservoir under the ground, and that's the fossil fuels. You can see this in the IPCC picture on the right. And if it comes to observations, they have to cover all of these reservoirs, but more importantly, also the fluxes between them. These observations should be global, and they should be standardized and, of course, continuous. And this is a big challenge for the respective infrastructures to have sustainable budget for providing continuous measurements. And as I've mentioned already, the data should be easily accessible, open, and fair. When it comes to ICOS, you have already seen in a very small picture this map. We are a so-called distributed research infrastructure, which means we have a lot of stations, a network of observations all over Europe. For example, these kind of towers, which are providing flux observations between ecosystems and the atmosphere, but also a lot of additional parameters like climate and radiation balance. We have these stations in many parts of Europe, for example, here in the very north. Then we have ocean stations that are mainly measuring the so-called PCO2, and we have also atmospheric stations like the famous High Mountain Station at the Jungfraujoch. And we have a lot of highly motivated scientists and engineers who even go in the very north up these towers to maintain the measurements, and who meet in conferences and meetings to work on the data and to improve this data. This was a very brief introduction into our infrastructure. ICOS has a history of about 15 years now, starting with a design phase. Then we went through a standardization phase and implementation phase. And now we are in the operational phase where we provide data and services. You can see our internal data flow on the left-hand side. So it goes via or from the measurement stations via the so-called thematic centers to the carbon portal, where the data are published, but it's also providing support for the data analyzers to scientists, and all the users can access this data very openly and fair. So we have, to summarize the standardized measurements, we have standardized data processing, a centralized quality control, a clear data provenance, data curation and archiving, a clear open data license, and we are also working on the data citation, because that's the other side of the coin of open data, that a proper data citation should give acknowledgements to the data producers. What's our cooperation between Europe and Australia? We have different frameworks for doing that. So we have a framework called JERI, the Global Ecosystem Research Infrastructure. And here, and we and another European research infrastructure, the European Long-Term Ecosystem Research Infrastructure, is connected to TERN, and I've seen some TERN people in the audience. So hello to Beryl and Mark. We have suggested or introduced this JERI already, where also Neon and from the USA and from South Africa, and also the Chinese Ecosystem Research Network are connected to us via a memorandum of understanding. And we have introduced this already to the G7 because we think that the connection between these more regional research infrastructures and the standardization and data sharing between them is creating a global infrastructure of, in this case, really big importance. Yes, I already mentioned that we have a memorandum of understanding in place for this connection, and we are hoping that this will also attract more ecosystem research infrastructures in other parts of the world, for example, in South America, or a Pan-African infrastructure. We also have frameworks for cooperation in the marine research, and the next speaker will definitely talk more about that. That's why I'm only briefly mentioning it. You saw that we are measuring PCO2. Our data are going to a global database called SOCAD, and we are also cooperating in the International Open Ocean Carbon Coordination Program, IOCCP. With that, we have, again, other European research infrastructures like EMSO-ERIC and Euro-Argo-ERIC in the boat. I think this is as well a very important cooperation. And finally, on the atmospheric side, we are a so-called contributing network to the Global Atmosphere Watch, coordinated by the World Meteorological Organization. And here we are, we have partners in Australia at CSIRO, which is running at Cape Grim, a similar station. But we also have, again, other European research infrastructures like ICOS and JiaBin here having a look at the atmosphere. And this brings me to a community of research infrastructures that we have established in Europe, the so-called ENRI community. This is a very nice picture of what this community is covering. It's covering the whole Earth system. So you have the different domains: land, ocean, atmosphere, and solid Earth. And you can see that there are many, many research infrastructures like ICOS, LTR, Actris, all the ones I have mentioned, and many more are connected to each other. We have a booth, an ENRI booth here in this meeting, and I think ENRI is a very good example of cross-domain cooperation of research infrastructures at the European scale. And if you want to have a cooperation with one of these infrastructures, I think ENRI is also a very good entrance point into this cooperation and into finding the right partners. Finally, I would come back to the quote of Klaus Hasselmann, this year's Nobel Prize winner in physics, who said, "I would rather have no global warming and no Nobel Prize." And this brings me to a topic that has also been discussed about the socio-economic impact of climate or environmental research and research infrastructures. The pictures show recent catastrophes, big fires in Australia, a big flood in Germany, where billions of euros were piled up as damage, and I think the damage in Australia has even been higher. So let me give a few remarks on the social impact of climate and environmental science at the end of my presentation, because it's difficult to discuss this impact. It's difficult because we are not always creating new wealth, but we are providing knowledge that might save humanity from severe losses. And I have cited a paper on the right that says even the difference between keeping the 1.5 degrees and 2 degrees temperature increase make trillions of dollars. It's really worth to read this paper. Of course, there are positive, not beyond the preserving of wealth, there are also very positive socio-economic impacts. It's the innovation in many fields, for example, e-mobility, regenerative energy, green hydrogen, many changes and many innovations that in a way are basically triggered by the information about climate change. But also there are, of course, problems with so-called stranded assets in particular in fossil fuel industries. And this may also lead to specific losses. And a colleague of mine who doesn't want to be cited once said, a coal miner's brain can't grasp any positive socio-economic impact of climate research. And this shows that it's important who makes an evaluation on the socio-economic impact and how this is done. One further remark is that economic damages like a burned house or a lost car, they can be quantified in money, but losses in ecosystems, in species, in biodiversity, in human lives and well-being can't be sufficiently quantified in money. And I think that's also an important aspect of or societal and economic impact. And I think we need really new approaches to look at them and not only try to monetarize the impact of research infrastructures. That's my 2 cents on that, and I'm thanking you for your attention, and questions and discussions are really welcome.
So are there any direct questions to Werner right now? There are some few questions in a chat, but they fit quite well actually to the panel discussion afterwards. They would address basically the Earth systems at large. There is a question by Ari. So
yeah, it's actually about the last comment from Werner that you can't put any monetary value for these things, but don't you think that could be anyhow one thing which we should aim towards, at least give some sort of generic idea for the different decision makers to balance, to think about the nature as an asset and thinking how much your asset goes down from different kind of investments, like in any kind of business decision? Or do you think this is completely impossible and cannot be done neutrally?
Well, I know approaches that are doing that, and I have been involved in this discussion since years, if not decades. But if imagine there is a plant species lost that might have some ingredient that will save us from a pandemic in 100 years, and then it's not there anymore. That's something you can't quantify now. So and this means that you can put billions and trillions on the table and say it's super important to keep biodiversity or keep specific ecosystems and so on. But the uncertainty is always really high. We could say the value and the importance is huge, but I wouldn't quantify it. Is it now 2 trillion, 5 trillion, or whatever? So that's my problem with that. And I have also a bit an ethical problem. There are things that we should not monitorize.
Okay. So thanks a lot, Werner. There will be some time to discuss those issues in more detail after the third talk right now. So I would suggest we move on to the next presentation by Michelle Heupel. She's the director of Australia's Integrated Marine Observing System based at the University of Tasmania in Hobart. Michelle has an extensive experience in working in marine sciences, focus on ecology, conservation, management of marine predators, which sounds very interesting and intriguing. Within IMOS, she's planning and implementing research infrastructure for a wider range of equipment for observation of the oceans. And I'm very much looking forward to Michelle, to your presentation. So the stage is yours.
Thanks, Roland. I think Werner is a nice bridge between Tim's talk and mine, but I will, like Tim, start off with a quick acknowledgement of country. I'm sitting here in Hobart, Tasmania, on the lands of the Muaninar people, and IMOS honors our traditional owners as Australia's first marine scientists, and we pay tribute to their traditional ecological knowledge and their perspectives as we work collectively to understand our marine environment. So if I can get my slides to advance. Why is ocean observing important? Well, we've heard a little bit from Werner about, some of the implications of climate change, and sustaining and managing our ocean territories really requires a lot of scientific information so that we can understand the variability and the changes that are happening in these systems. In Australia, our ocean territory is actually twice the size of our land territory. So it's a very big job for us here. Our oceans are vast and valuable and a really important part of our nation. Our oceans regulate and drive our climate. They store heat, they absorb carbon dioxide, they shape our coastlines. The waves and the action from storms change, where the shape of our coasts, where the sediment is and where it moves. We're also looking at things like sea level rise that are going to cause inundation into our coastal areas and change the shape of our coast that way and the shapes of our cities that we live in. Our oceans also provide habitat for iconic species and other species that we rely on for food. So in short, our oceans are critical to our weather and our climate. They're critical to our way of life, our food security, and ultimately our well-being. So understanding them, taking care of them, and sustainably manage them is critical. So introducing IMOS, we're a national capability inside the NCRIS program, which you've heard quite a lot about this week. We're a collaboration of 7 main partners and 4 associate participants that are spread around the country to deliver this national scale program. And we're based here in Hobart at the University of Tasmania. We're a research infrastructure with really a singular goal, and that is to deliver benefits to Australia by undertaking systematic, sustained, and scientifically robust observations of our vast and valuable marine estate. And we structure our program around trying to use the observations we collect to deliver benefit to society. Where do we sit in the global context? So IMOS is one of 13 global regional alliances in the global ocean observing system. So we have very direct and regular links in with the rest of the global ocean observing system community, including EuroGOOS. We work with our colleagues in Europe and the US very closely. We also obviously intersect with the oceans that connect into Asia and over towards Europe, as well as we work with our regional partners in understanding the system here. I don't have a lot of time to talk about all of the IMOS capability that we have, that we're operating. We have over 60 different sub-facilities that are deployed around the country. And this is a range of different infrastructure, from things like deep water moorings in the Southern Ocean to understand what's happening there and how conditions in the Southern Ocean are changing and how that might affect our climate. We use ships of opportunity to collect data in remote areas and on regular transects. We have profiling floats that I'll talk about a little bit later, underwater vehicles that are also collecting observations. We use animals to collect observations. So we have seals that have tags on them that are collecting data. We're also tracking fish along the coastline to see where they go and how they respond to changes in the environment. We use satellite remote sensing, coastal radar, and a range of other pieces of infrastructure around the nation to try and understand this very large marine estate. All of the data that we collect comes in and goes into our national repository, which is the Australian Ocean Data Network. So every IMOS observation that we collect is delivered using FAIR principles. So it's discoverable, it's accessible, usable, and reusable via the AODN. But we also contribute to a number of international programs. So some of our data is delivered directly to the World Meteorological Organization and goes into global weather and climate modeling. And then we feed into various international programs. One of these is the one that Werner mentioned earlier. So we provide data into SOCAT, and that data comes from ocean acidification monitoring that we do at some of our moorings, and also data that comes in from air-sea flux moorings that we operate. One of the things that we're trying to do with the data and the observations that come in from IMOS is actually transform that data into information. So we're working to integrate the observing data and contribute that into a range of these programs. So for example, as I said, we contribute data into the big global programs. And a lot of these data end up being used for weather forecasting. They're used for climate modeling to help understand what the conditions are, what the trends are, and how things are changing through time. Our data are used for emergency services, so search and rescue programs. We'll use some of our data when they're trying to find people, particularly using things like ocean radar to understand what the currents and the potential movements of people or items might be. We underpin industry operations, so fisheries agencies and individual fishers, as well as the Navy and others who have to operate on the water, rely on our data and data products to understand whether it's safe for them to operate and help them make decisions. And then, of course, we have oceanographic modeling that we contribute to that helps us understand what the dynamics are in the system. The theme of this talk, I think, is around challenges. And so I want to talk about some of the challenges and opportunities and the things that IMOS is doing. Australia is a very coastal nation. Over 90% of Australians live within 100 kilometers of the coast. And recently we've had some very interesting changes to our coastline. We've had some rather large storms come through and change the shape of the coast. To be prepared for these sorts of events, we need to understand the implications of the ocean processes. We need to know what these broad scale processes are doing, how they will change over time, and what the potential implications are, so that we can manage and mitigate as best possible. And there are a range of people who need this information. This isn't just research scientists. In this blue bubble here, you can see it's everyone from the Bureau of Meteorology through to city planners, finance and insurance companies who, value the things that we have on the coast, our industries and ports that operate in the coastal areas, and all the way down to, our communities and homeowners who live in the coastal areas. So through data sharing and integration with other research infrastructures, excuse me, we think that we can offer some new approaches. And there are some real opportunities to create societal benefit and impact for Australia and our neighbors through transdisciplinary approaches. I'm going to cough the whole rest of the way now, sorry. So implications of coastal change. Coastal erosion is already an issue in Australia. It's an issue in a number of places around the world. I'm sure you're having these issues in places in Europe as well. You can see some pictures here, some of the East Coast low storms that have come through and caused some very unexpected and significant damage to our coastlines. We also have sea level rise, which is going to lead to inevitable inundation in our coasts. These processes, as I said, they affect our homes, our livelihoods, and our communities. We know they're going to change. We know these systems are coming. The predictions are that waves and currents in the Southern Hemisphere will only become stronger in the next 10 years. So we know there will be more of this to come, but we don't know how much. So we need more data and better data to help understand. Coastal inundation, as I said, is also an inevitable issue with sea level rise. These are some shots of various cities around Australia where you can see the projected coastal sea level rise. These are high tides in 2100 based on a sea level rise of about 0.7 of a meter. So we have some very significant challenges coming if this is the reality that we're to face. And with all of these homes and businesses and other pieces of infrastructure on the coast, we need to think about how we plan for that, how we manage for it. So one of the things that IMOS has been doing is working to better understand the wind and wave activity. So we've just recently published a new global ocean wind speed and direction data set, which is aimed at defining the impacts of extreme winds and using that to assist maritime industries with their operational decisions and increase navigational safety. We're also trialing some low-cost wave buoys to determine their suitability as long-term monitoring for coastal waves. They can serve as early warning systems in places like Pacific Island countries where they want to know when large waves are approaching. So they have a range of potential uses of this infrastructure if it performs as well as, as we hope. And when we can connect up coordinated programs of these buoys at scales that are relative to the oceanographic processes, we can then start to better help understand the broad scale issues and the changes and the patterns that are happening in our systems. So that's a little bit about things that are happening on the coast. What about the open ocean and weather? Because the ocean is very connected to our weather. One of the programs that we're involved in, and Werner mentioned this briefly as well, is the Argo program. So Argo floats are deployed in oceans around the world. Australia deploys floats, not surprisingly, in our waters and in adjacent waters. And these floats are measuring salinity and temperature in the top 2,000 meters of the water column and profiling and sending those data back to help us understand what the conditions are, where the floats are moving. And these are floats that last for periods about 5 to 7 years. So we get really nice long time series data from these individual floats. Australia is a major contributor to the global Argo program. This map now is a year old. I realized this morning when I put it in here, but you can see that Europe is also a contributor into this program, and there's a range of European nations that also make individual contributions. So this is a really amazing globally coordinated program that deploys floats at a broad scale to try and help us understand and in a global manner what's happening in our oceans, how it's changing, what the trends and patterns are. And due to the ocean's ability to store heat and play a strong role in our climate, understanding what's happening through this program is really critical to understanding our seasonal long-term climate, but also our seasonal and longer-term weather forecasts. So these data really enable climate and ocean modeling and forecasting at national, regional, and global scales. Another thing that IMOS looks at as the world continues to change is trying to understand extreme events. And in our case, one of the main ones we are looking at is marine heat waves in coastal waters. These events are becoming more and more common, unfortunately. And for us, one of the big issues that you will all have heard about globally and is a similar issue in other places is the impacts on habitats like coral reefs, where we're experiencing bleaching and other associated impacts as these warm weather events come in and affect the animals and the species that live in these habitats. So one of the things that we do is we deploy gliders when we anticipate a marine heat wave event occurring. And these gliders can then go in and profile the water column and tell us where the warmest water is, how deep it's penetrating, how far it's spreading, which helps us then anticipate and understand what the potential impacts of that marine heat wave are. So how pervasive will it be and how much damage can we anticipate after the event has abated? A second set of challenges and opportunities for us beyond understanding all of these broad scale patterns is, I guess, something that we call ocean information services. And I suspect this is an issue that others will have and will continue to grow. And that is that as we work to create societal benefit and we work to be relevant within and beyond the research community, more and more non-specialists will want access to the information that we have. So people who work in industry, people who are resource managers need information products to help them make decisions. And they're not experts. They don't necessarily know how to process the kinds of data that we deliver. So we need to be thinking about how we convert the vast amounts of data that we collect into information that these people can use. The last one for us is continuing to explore new technologies and new approaches, making sure that we are doing things as effectively and as efficiently as possible, considering new approaches and new methodologies that come along, like environmental DNA, to help us do what we do more effectively and efficiently, as I said, so that we can drive down the cost per observation, which means we can do more and we can spread our resources farther. Finally, some conclusions. I apologize, I've been talking too much this afternoon. The ocean plays a significant role, as I said, in the Earth's climate, and observations of ocean conditions and rates of change are critical to our understanding of the system. Understanding broad-scale coastal processes and storm events are going to have serious effects on how we de-risk and how we mitigate to make sure that our homes and our cities and habitats are safe in the future. As climate continues to change, we're going to see flow-on implications to species and habitats. As Werner said, this is going to include species loss, range changes, range expansions, changed migratory patterns, and more. We need to understand the system so that we can anticipate where these animals are going to be and how these changes are going to affect them. Finally, we rely on the ocean for recreation, industry, and for food. Long-term sustained observing and research are really fundamental to understanding how it's changing at regional and global and international scales. And I will say thank you and stop coughing at all of you.
Thanks, Michelle. So to give you some time to breathe, I would suggest we start now with a panel discussion. There were some questions in the chat, and I would also like to potentially go into the same direction with the first set of questions. So I think one of the common issues that you described is that all the infrastructures, they are doing observation of different components of the Earth system. The observations, you produce huge amounts of data, and the goal is also to use this data to develop models, to make prediction. But talking about Earth systems, there is a need to integrate those different systems. Can I ask you, I would start maybe with Tim, how do you, from the perspective of geosciences, the integration of different disciplines, in particularly integration of data, standardization of data, how do you approach this issue?
Yeah, thanks, Roland. Look, it's a really important question. I guess my feeling is that there's a lot of work already going on internationally within disciplines about how to manage that. So, I gave an example in the chat in our space of One Geology, but there are a number of other groups that are working on standards. And trying to understand how our sort of discipline-specific data should best be managed. And that's having a huge impact. I think the real challenge is when you try to get into that sort of unforeseen, opportunistic, interdisciplinary research that maybe we've never really planned for and we don't really see a reason for doing yet, but all of a sudden it becomes critical for whatever reason, and we've never really thought about why or how to mash up those data sets. And I think that is a much bigger challenge. I think the other challenge that organizations like some of ours have is that we are, effectively, we deal with a whole bunch of federated partners that have their own drivers and their own history and their own, reasons for doing things the way they do. And that really does create an enormous standardization challenge. And some parts of our discipline are much more advanced than others. But I think that there's a broad recognition now that we need to work together to agree on standards and to provide data in a format that can be discovered and used.
So there was a question in the chat which also addressed basically this issue with specifically incentives. So maybe to Werner, what do you think? What would be this incentives for you as a data infrastructure provider who is interested also in not only collecting data but also making this data available? What would be the incentives for you to make the community also make them aware that data reusability is important across different disciplines?
Well, we are working on that across the discipline. ICOS itself is multi-domain, so we have ocean people, we have atmosphere people, we have ecosystem people who all have their traditional way of sharing data also globally. For me, it's always interesting to look into the different global systems and into the different European systems. And there are a lot of incentives. The most important incentive is, of course, that we can do better science with sharing this cross-domain data and making data easily findable. I think it should also make any operator of a research infrastructure proud to see how the data are used under many, many purposes. In Europe, we have this ENVI community, which is supported also by the European Union in so-called cluster projects, as the other bigger domains like physics, astronomy, and so on are also. And inside these cluster projects, we have traditionally a focus on standardizing our data streams. So that's something that is already going on since a decade, almost, over several cluster projects. And we are now commonly developing the so-called ENVI Hub, which is a common data entrance point where you can get data and services from different research infrastructures. And I think, as I said, the incentives are large, also the societal impact, as I mentioned, and the societal necessity to have this easy accessible data are large. And I think that's challenge enough or motivation enough to do it. And I think, yes, as I said, globally, mainly inside specific disciplines, and at least in Europe, across disciplines with the ENVI community, there's a lot of progress going on.
Yeah, thanks, Michelle. Your perspective?
Yeah, I think there are a lot of reasons for all of us to share data now, and I think the world is changing in that the journals are all making people make their data sets available for the papers that they're publishing. One of the conversations that I have with a lot of people here is that when we combine our data and we make our data interoperable, we can do more. We can answer more complex questions. We can, for industry who wants to know, wants the models to be better, or wants the predictions to be better, well, the more data we can get into those systems, and the more precise they can be, the more accurate they can be, the better the information that comes back to them. So if industry has data that we can feed into the models, then, and we know they rely on our models to make their decisions, then they win. There's a benefit to them in sharing that data and having us use it to improve the models. So I think it's about finding the feedback loops for people and saying, it's not just you giving us something for nothing. It's you contributing into the broader community. And there are rewards that come back to you for playing your part in that space.
Yeah. Thank you. That's
Roland, can I just add one more thing that's occurred to me? And a couple of people, I think both Michelle and Werner both touched on it, but one of the rewards that we could look to incentivize this is that culture change that comes with people recognizing that data is as important or more important than the traditional publication. And, that's a whole academic cultural change piece that's really hard. But if we can get data citation as being just as critical or just as important or more important than your Nature paper, then people will be pushing all their data out the door as quickly as they can get it. And, it's hard, but it is a game changer.
Yeah,
Absolutely.
I fully agree. Yeah. There is a question also in the chat, which potentially goes into the similar direction. It was about the proactivity. How proactive do you think a research infrastructure can be in tackling climate change? But it would be also this proactivity, not only towards climate change. One aspect would be providing data to address different aspects. I suppose there is quite a number of proactivity in having cutting edge technology, observation systems that are already in place. This is one of the key roles of research infrastructure, to have them in place. But also the next step is providing this data, addressing climate change, but also addressing the society at large. It potentially addresses the question that was asked by Ari before, economic value of this research. So there are many different aspects. How proactive do you think research infrastructure should be in this context? Should we start with Werner?
Well, there's a good news and a bad news on that. I think the good news is that we have a fantastic scientific community, I think, in all of the research infrastructures, and they have brilliant ideas, and they bring a lot of innovation. One example out of ICOS is that we have the challenge, and this is also connected to the societal challenges, to go closer in our observations to the fossil fuel emitters. And we are really happy that we got funding for a new project that has just now started. And this is a pilot on city observations of greenhouse gas emissions. And the community is super enthusiastic to develop new things there. This is really the good news, that we can get funding for this enthusiastic community to really push the innovation towards better observations and to new technologies. The bad news is that we have definitely a problem in making this innovation operational. And that's the big challenge, because at a certain point we are meeting our bureaucrats who are sitting on the money, and they, if we say, okay, hey, we have a brand new super technology, and we need some money to make this operational and sustainable for a long time, then it goes the way through ministries, through funding agencies, through lots of discussions, and so on and so on. And that's the point where usually the innovation got stuck. And I think that's something we we definitely need to talk to our governments, our funding agencies, to find ways to make innovations operational.
Michelle, what do you think? How proactive is the marine community?
Look, I think it's an interesting question from a research infrastructure perspective, because it really should be the research scientists that are the people that are out there being proactive and that are driving this. And I think our role is, to underpin that and provide them the data that they need, and to be listening and responding to what they want, where possible. So if there are new streams of data that they need to improve the models, then if we have the capability to deliver that, or bring that into our programs, I think that's where our role fits. It's responding to what the community and the people actually out doing, building the models and doing the science are telling us this is the critical piece that we need to take the next step. Then our role is to try and help them, get that critical piece. That would be, I think, how I would see it.
Mm-hmm. Tim, if I may add another aspect of this proactivity of research infrastructure. So what's maybe an interesting topic, this proactivity towards younger generation training. Looking at Fridays for Future, this young generations interested. They are more and more interested in climate issues, in environmental issues. Looking at the recent vote in Germany, young voters voted completely different than the senior voters, to put it in this way. You could imagine how. Is there also this proactivity towards, is there a need? I think there is a need, proactivity towards intergenerational, specifically training young scientists. Is there a role for research infrastructures on national, but also global level?
I definitely think that there is. I think it can be a challenge for our funding models sometimes, because sometimes the way we fund it is not really to support that sort of training. But, it's interesting in Australia at the moment. Look, I'll give you two little short anecdotes. One is something that I touched on in my talk about the role for research infrastructures. And I mentioned that our role has changed and that we're seen as this honest broker of information, and it goes towards what Michelle was just talking about. Mm-hmm. The example that I was actually referring to was when there was some fracking happening in Queensland and New South Wales a few years ago. A lot of the farming communities were very worried about what this fracking and exploration for coal seam gas and things was doing to their groundwater systems. They didn't trust the Commonwealth government to put monitoring out there because they thought that they were in the pocket of industry. They didn't trust industry to put monitoring out there, but they did trust AuScope. So we were actually approached and we were asked to put seismometers out. We were asked to put tilt meters, a whole bunch of different infrastructures out there. And interestingly, the way we ended up doing that was through our AusSys, which is our seismometers in schools program. So we were actually deploying these instruments with the schools in those regions, and we were letting those communities run those instruments, and they're research quality instruments. So the data that they were producing was feeding into our national networks and was being used by researchers, but it actually provided a community engagement opportunity. It provided a data set that this community actually trusted more than from anyone else. And it helped us with, one of the existential threats for geosciences really is that we're seen as this dirty mining, we just go and dig up the countryside and destroy the planet. Whereas in fact, we play a critical role in this conversation around climate change, because without understanding a lot of the geoscience components, we can't have a meaningful impact on mitigating climate change. So we're really struggling to sell that message to young potential students, because they see geoscience in Australia as being just to do with digging up coal, which is absolutely the tiniest, minutest component of what the science is in this country. So that's a huge challenge for us that we think is an existential threat that we have to address.
Mm-hmm.
Yep. Can I make a brief remark on this? I think the advantage of distributed research infrastructures, and most of the environmental research infrastructures in Australia and in Europe are distributed, is that they usually have a large scientific community because many universities and science institutions are involved there. And I think that's a treasure we really can build on. And besides having direct talks to the Fridays for Future movement, because there is also a movement called Scientists for Future that connect to that, we have, I think, a good way to get research infrastructures even into the university curricula by providing our data and activating the scientists from these distributed stations to use the data and to show the research infrastructure and the work that we are doing in their teaching.
Mm. Yeah, I fully agree. There is a role of research infrastructures in training the next generation. What's particularly, coming to a slightly different topic, what's particularly interesting or important for research infrastructures in this domain, in environmental sciences, earth sciences, it's this international, global, so many issues, climate change, but many other issues, those are global issues, obviously. Werner, you mentioned this ENVRI initiatives cluster of research and environmental research infrastructures in Europe. Is there also a need for ENVRI global, or how would you approach to make this kind of a ENVRI global and make this research infrastructure on a global scale to interact, which fits well into the mission of the RI-VIS project. So making infrastructures visible across the globe, bring them to work together. How would you approach this issue?
Ideally, yes, it would be wonderful to have a global ENVRI, but this might be huge and not manageable. What we have and what we should build on is this domain-wise global integration. I gave the example of the JERI, of the global ecosystem research infrastructure, where we are connecting, let's say, in a specific land ecosystem related way. And there's a lot of standardization, a lot of data harmonization, a lot of data sharing, also via FluxNet to do. And I think the same is going on. You saw the global Argo floats, you saw the SOCAT map is going on in the ocean, and the same is going on in the atmosphere. And there are in climate science a few organizations that are trying to coordinate this interdomain. For example, the global climate observing system, ICOS, that is defining the so-called essential variables. And there the domains are coming together and trying to define a global observation system. That's really important. And well, in an ideal world, we would have a global ENVRI community, but I think practically we will go, at least in the next years, through the domain-wise integration. But yeah, let's work on it.
Mm-hmm. So what would be the perspective from Australia on bringing Australia closer to Europe, and not only Europe? So Tim, what would be your perspective?
Oh, look, I agree with Werner. It would be fantastic. You know, I have had a fair bit to do with ENVRI over the years, and I'm amazed at what they've been able to achieve within that community. And I would love to see that rolled out as an international program, but it runs the risk of becoming enormous, and I wonder how you manage that. So I do think that there's a role for some more sort of, again, discipline-specific approaches that that if they're designed with an overarching strategy, then maybe they become exactly what you're talking about. But to try to create something like that would be challenging.
Mm. And then from the marine perspective, Michelle?
Yeah, I think in the marine perspective, we've recognized for a while now that we have to be a bit more connected, because our ocean is somebody else's ocean as well. It's all connected. It doesn't have the hard boundaries that a continent does. And so, we've been working collectively, at regional scales to try and understand some of the issues, because it is all connected. And I think that puts us in a slightly different perspective. And we do have these big global programs like the Global Argo Program, and we, contribute in data from the world's oceans into big international, programs that are looking at trying to understand these things at scale and understand them at a global or a regional, ocean basin scale. So, yeah, I think there's more of this to come. I think, we will get, when you were talking about the training, I was thinking about how automated, some of the technology we use is going to become. In the marine, there'll be a lot of disappointed marine students in the future who think they're going to come and do lots of diving. That's getting phased out. We're getting automated ways to collect these data. So the more of that sort of instrumentation that we have, the more data we have coming in, the easier it will be to be connected, and the easier it will be for us to be interoperable and share and learn from each other. So I think we're on that path. There's a long way to go. And, as Tim and Werner both pointed out, these things have the potential of, becoming bigger than Ben-Hur, but I think we have to walk in that direction, because we can learn a lot from each other by working together in that way.
Mm-hmm.
But in fact, we have interesting things that are already integrating our data. I'm thinking about the Global Carbon Project that gives every year the global carbon budget. It's coming closely before the COP, and they are integrating the data from all the emission inventories, from ecosystem fluxes, from ocean fluxes. They are looking at the atmosphere. They are doing inverse modeling. So this is one very good example where, even if we are mostly organized domain-wise, where in the end all the data are coming together.
Mm-hmm. Yeah, I agree. The domain-wise integration, it's already in progress. Integration across domain, it's a challenge, but it's still needed. I would also, if there are questions also from the audience, so please also raise your fingers, raise your hand, and I would also open the panel also now for questions from the audience. There is a question by Natalie.
Hi, just a quick one, kind of similar to your talk, this idea about a global ENVRI. In Europe, there's the European Open Science Cloud Initiative, which has been touched upon by some speakers already in previous sessions. I was wondering if, from your perspective, something similar might be useful globally, or have you got initiatives in Australia that are analogous to this?
Look, from my point of view, a lot of these European programs like the Open Science Cloud and ENVRI, are kind of almost stepping into that global role anyway. So many Australian research infrastructures are engaged with those communities and are providing data into them or collaborating. We're doing it around geochemistry, we're doing it around some Horizon 2020 projects. There's a whole bunch of stuff that's happening in Europe that is already driving this internationally, and probably vice versa as well. So I think it probably is already happening to a large degree. It's probably just not considered as a global infrastructure in the way that, you know, we use that term in some other aspects.
Michelle, do you want to add something?
Yeah, I would just agree with what Tim's saying. I think, you know, we contribute into a lot of global programs. And one of the things that I think about a lot when we talk about starting new initiatives like this is, are we contributing or are we duplicating? You know, and if there are already existing mechanisms where we can contribute in that are operating at scale, I think we're better off just joining in than having sort of two things that may or may not talk to each other, may or may not be compatible. I think we need to be, you know, there aren't enough resources to go around that we should all be pushing each other out of the way. I think we should just work collaboratively.
Okay, thank you. There is a question. So Nick is raising the hand. So Nick.
Thank you, Roland, and thank you, speakers, for some excellent talks. I can just start by saying I cannot agree more with Michelle. You know, cooperation and collaboration is certainly the way forward. And I think it's also worth mentioning the GOOSE initiative within the marine sector, where there is an awful lot of coordination around standards, data standards, and so on. And this is really, really important. It's developed regionally, but there is coordination at the global scale. And on the marine side, that's really, really important. I actually have two questions, but I'll start with one actually directed at Michelle. You mentioned in your talk, you know, the increasing interest from non-specialists to gain access to a lot of the huge amounts of data that's available. And very often this is very specialized data, and especially when you start getting into the genomics and so on, this is not straightforward to analyze. So I guess there's a risk of misinterpretation, but does this not offer an opportunity, if not a responsibility, to actually offer analytical services? You know, how to interpret that data in a particular context. So for the research infrastructures, there's probably a space there to develop.
It certainly creates a lot of opportunity. The question is whether it should be the research infrastructure who is, you know, who's the mechanism for delivering that, or whether it should be some other entity. So, you know, a good example from Europe is that you have Copernicus, which is, you know, a program that's just purely designed to deliver the data and, you know, build the models and put it out. They're not the people collecting the observations. They're the people who are, you know, dealing with the data and processing it and doing amazing things with it. So, you know, where does that, whose job is it? Where does it fit? We don't have Copernicus in Australia, so we're now looking at, okay, what do we do to try and fill this gap? Because, you know, there are fishermen who want this data to make their operations more efficient, right? And so they can be more targeted in where they're fishing. That's good for all of us because it's less bycatch, it's less fuel for them operating on days when they're not going to catch. All those sorts of things are benefits to the fishermen, but also to us, you know, in looking after the ecosystem. So yeah, there are a lot of trade-offs in there and a lot of questions about, yeah, should we be doing it, or who should be doing it, or how do we get that product into the hands of the people that need it?
Roland, may I be so rude as to take the opportunity to ask another question?
Go ahead, please go ahead.
Thank you very much. This is actually directed at Werner this time, and his comment about when we propose things, it ends up in a very, very long discussion with stakeholders, and very often it actually kills off an initiative. I had an interesting conversation recently where the question was asked, should the conversation not be going the other way around? As scientists, we are often telling our politicians essentially what data they need and what questions they want to answer. And this usually means they're not prepared for it and they don't know what to do with it. Should the conversation be going the other way around, in the sense that we should say to them, what do you want? And then we design the technology and gather the data required based on their needs and what they actually want to know, rather than our assumptions.
Yes, definitely. We have recently a bit worked over what we call the value chain. So usually a value chain towards society is that an infrastructure provides data, then scientific community generates knowledge, and then the knowledge is transferred to the let's say more societal sphere for politicians, for example. As I mentioned earlier, the COP is yearly informed about the Global Carbon Project. But exactly, we are not always seeing what these services should be, and we have now more designed, let's say, a double circle. So it's starting with the societal demands or requirements, the questions that the societies have, and science is in a way translating this in possible observations, and then it goes through the research infrastructure cycle, providing specific data or the required data, and then science again makes the services and the information of the society. And having this double circle permanently running would, I think, increase the impact of the research infrastructures, would improve the societal or climate services, and it would also in a way improve our discussions with the funders and stakeholders, because we can clearly show the necessities.
So in other words, we need a much better platform for engaging with our politicians.
Yes, yes. For example, in the city project, we will have a network with city representatives, and we will ask them, what kind of information do you need? We will, of course, have our gadgets that we will play with, and we will have newest technologies. But in this kind of cycle or double cycle with the cities, we might find out this is a super nice high-tech new gadget, but it's useless, and that's, I think, this conversation or this engagement should go, that we listen to the requirements, that we of course translate them into observations, but we also should reflect, is this only motivated by our scientific interest or technological interest, or because it's new, or is this really something that we are developing and implementing because it's providing the right services.
Thank you very much.
Maybe to continue on that, Tim, addressing politicians in Australia, how?
I don't want to touch that.
Okay. Okay.
No, look, I mean, it's a really good point. It's a difficult question. I don't know the answer. I honestly don't. I don't know the best way to engage with our current leadership in this country around this very challenging and politically charged debate. I would like to I would like to jump back just to Nicholas's question that he posed to Michelle very, very quickly, and that's around the data. And I think there's another challenge there as well about making raw forms of data available, because if you make very raw forms of data available, it facilitates certain types of research that are not able to be done on data products. But a lot of research infrastructures and government organizations are quite risk averse and don't like to make that really raw data available, because they feel if they don't do all the QA/QC and stuff on it, then they're opening themselves up, or they're opening up to misuse, and they don't like to take the risk of that misuse. I think that that's a real challenge for us as well. And it's a challenge that AuScope sees in the geoscience space, between the very raw data we try to put out and our colleagues at Geoscience Australia, who are more interested in putting out more refined data products, because they don't want to open themselves up to the perceived risk of putting out very, very raw data straight from instruments. I think that's a challenge going forward as well.
Yeah, that's a really good point. Looking at the time, I would like to thank the panelists for the discussion. So unfortunately the time is ticking. We need to close. I think you clearly demonstrate that research infrastructure address an important gap. There is, looking at your presentations, there is a lot of interaction across, interdisciplinary, so across different continents, but also across different disciplines, which is important. And I'm looking forward to continuing the discussions. And I hope also this, that RI-VIS as a project could bring you together, could put at least a small piece in this puzzle to bring you to continue the discussion, to integrate different disciplines and keep the discussion going. And I'm pretty much looking to the future discussions. And as such, thank you again. Thank to the panelists. Thank to all the participants. It was I enjoyed the session a lot, and I'm looking forward to the next steps. So thanks a lot.
Was a pleasure.
Thanks, Roland. Thanks, everyone.
Thank you.